Let us look at proposition number 17 of book 12 of Euclid's Elements. The proposition says, given two spheres about the same center, to inscribe in the greater sphere a polyhedral solid which does not touch the lesser sphere at its surface. Okay, let's see how we can build such a polyhedral solid. So we are given two spheres about the same center A. Now we cut these two spheres by any plane through the center. So just imagine we are cutting it through using a plane through A. Now that plane is going to intersect these two spheres in the form of a circle. So this is the circle of intersection and this is the circle of intersection with respect to the outer sphere and the inner sphere. Now let's mark some points on that. So let's take a random point B. And now for that next point, we take the opposite end of B and mark it as D. Similarly, C. So basically, we are taking these points in such a way that if we join BD and if we join CE, they are perpendicular to each other. Now, similarly, we mark points on the inner circle as well so that we can refer to them. F, G, and H. Again, we have chosen these points so that we don't have to again use another set of points to for some other purpose as well. So here G is on BD itself. So now from G, we draw a line parallel to CE and let's mark this point as I. Now we start bisecting BD circumference. So the midpoint of the circumference BD is E. Now this BE is not less than BI. So we now bisect the circumference BE. We get L. Now BL is also not less than BI. So now we bisect BL to get K. Now BK is less than BI. We take BK and repeatedly mark the points on the circumference. Now we don't require this I, so let's hide it off. So BK is equal to KL because K is the midpoint of the circumference BL. Now from L again we measure off BK. So we have M. Now we'll restrict ourselves to only this quadrant because then for the remaining quadrants it's more or less a repetition. Let's join KA and extend it to the other end. So we end up with KN, which is another diameter. Now these are two diameters of the same circle. So they are equal to each other. Now what we'll do is take a point or we'll draw a perpendicular from A perpendicular to the plane BCD and we will end up with OA. Let's mark that point as O. From K through O, we cut the spheres using a plane so that we get a circle of intersection KON. But to begin with, we are just interested in this quadrant. So let's just draw the semicircle. Similarly, we cut the sphere through BO to get the semicircle BOD. Now, the semicircles BOD, KON, KED they are all equal to each other because they are on the same or equal diameters, which means that the segments that we have marked here, they will be there on these semicircles also in the same magnitude and same multitude. So if we have 4 segments here, here also we will end up with 4 segments. So let's cut off from BO segments equal to BK. So P, Q, R. And similarly on KO as well. S, T, U. And let's join these points. SP, TQ, UR. And the points BP, SK, PQ, TS, RQ, TU, RO, UO, and DK. So we have got a polygonal figure inscribed on the outer sphere. And now we join each of these points S, P, Q, T, R, U with A. So SA, PA, QA, TA, RA, UA. So what have we got? We have got pyramids, 3 pyramids with quadrilateral base and 1 with a triangular base. So in a way, we have formed a polyhedral solid which is inscribed in the outer sphere. We have not done it completely because we have to repeat this on KL, on LM, on ME, and we have to repeat the same process in all the other quadrants. Once we complete that, we would end up with a polyhedral solid inscribed in the outer sphere. Now, we have to prove 2 things. One, that the points KBPS lie on the same plane, and that the quadrilateral KBPS does not touch the surface of the inner sphere. So let's see how we can do that. First, we drop perpendiculars from P and S to the plane BCDE. When we drop those perpendiculars, they will fall on the diameters BD and KN. So let's drop those perpendiculars and let's name those points VW. And let's join VW as well. PV is equal to SW because remember PB is equal to PK is equal to SK. So we are dropping perpendiculars to a plane from the same height. So PV is equal to SW. And BV is equal to WK because BP is equal to KS. Now, we also know that AB is equal to AK, radii of the same circle. And BV is equal to WK. That means AV is equal to AW. Now, in triangle ABK, because of these equalities, we have a proportion. BV is to AV as KW is to AW. So that means WV is cutting the 2 sides of a triangle in proportion, which means that WV is parallel to BK. PV and SW, they are both perpendicular to the plane BCD, which means that PV is parallel to SW. Why? Because perpendiculars to the same plane are parallel to each other. So we have shown that PV is not only parallel but also equal to SW. WV is parallel to SP and WV is parallel to KB. which implies that SP is also parallel to KB. And BP and KS join the ends of SP and KB. So quadrilateral KBPS is in one plane. Similarly, we can show for SPQT, and similarly TQRU are also in one plane. And we know a triangle is always in a plane. So it is also in one plane. Points KSPB with A forms a pyramid, a solid. Similarly, SPQT, TQRO, URO forms a pyramid. These three form a pyramid with quadrilateral base, whereas the top one forms a pyramid with a triangular base. First part is over. Now we have to show that the quadrilateral KBPS does not touch the surface of the inner sphere. To do that, we drop a perpendicular from A to the quadrilateral KBPS. So draw AX from the point A perpendicular to the plane of the quadrilateral KBPS. So let's do that. So we have AX. And now we join KX and BX. Here, AX is perpendicular to both BX and KX. Why? Because AX is perpendicular to the plane and BX and KX lie in the plane and meet X. AB square is equal to AK square. Why? Because AB is equal to AK, since they are the radii of the same circle. AB square is equal to AX square plus BX square, and AK square is equal to AX square plus KX square. But since AB square is equal to AK square, that means AX square plus BX square is equal to AX square plus KX square, and AX square being common to both, we can say BX square is equal to KX square, which means BX is equal to KX. Similarly, we can show that PX is equal to SX is equal to KX is equal to BX. What does this mean? It means that if we draw a circle with the center at X and radius as BX, the circle will pass through P, S, and K as well. So let's draw the circle. So KBPS is a quadrilateral in a circle. BK is greater than SP. Since BK is greater than WV and WV is equal to SP. And since BK is equal to KS is equal to BP, that means KS and BP are also greater than SP. BK square is greater than 2 times BX square. Why? Because KBPS is a quadrilateral, BX is the radius, and KB is greater than SP. Draw KZ perpendicular to BD. BD is the diameter of the circle, outer circle. So let's draw that perpendicular KZ from K. So here BD is less than 2 times DZ. BD, the diameter, is greater than 2 times DZ. 2 times DZ is naturally greater than BD. So we are saying BD is less than 2 times DZ. And BD is to DZ. BD is to DZ as rectangle BD by BZ is to rectangle DZ by Bz. So basically this part is coming with a little construction, which I have not shown because it becomes too messy then. Basically what we are doing is we are drawing a square on Bz and we are completing the parallelogram on DZ. When we do that, we get this proportionality. Now, because BD is less than 2 times DZ, that means because of this proportionality, rectangle BD by BZ is also less than 2 times the rectangle DZ by BZ. BD by BZ is equal to BK square and rectangle DZ by BZ is equal to KZ square. So we have BK square is greater than 2 times BX square. BK square is less than 2 times KZ square. So which means that KZ square is greater than BX square. BX square plus AX square is equal to KZ square plus AZ square. Why are they equal? Because bx square plus ax square is ab square, kz square plus az square is ak square. And we know that ab square is equal to ak square. So these sums are also equal. And here kz square is greater than bx square. That means to maintain the equality, az square has to be less than ax square. So az square is less than ax square, which implies ax is greater than az. So if ax is greater than az, that means it is much more greater than ag. So that means the quadrilateral does not touch the surface of the inner sphere. So we can say polyhedron does not touch the lesser sphere on its surface. So that is proposition number 17 of book 12 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.